Hello there, Mr. Sutton here, bringing you this Pre-Cal Honors 9-1 lesson on intuitive limits, finite. In this one, we're taking a look at finite limits using a graph. For a warm-up on this one, consider the function x squared minus x over x minus 1. Two questions for you. First off, what is f of 1? And then, using a graphing calculator, what's the y value f of x approaches as the x value gets closer to 1? So pause the video and try both of these out. Alright, let's see what we came up with for f of 1. So we just have to plug 1 into the expression here. So that's 1 squared minus 1 over 1 minus 1. That's really 1 minus 1, which is 0, over 1 minus 1, which is also 0. And this is kind of interesting. So if we were dividing, say, 1 by 0, we know that would be undefined. And 0 divided by 1 would be 0. But what happens when you divide 0 by 0? So we're dividing by 0, so in general that's definitely some kind of undefined, but it's a little bit different than the ones we've seen before. Let's now figure out what value this function is approaching as we get closer to 1. We have to do this because we don't know what the value at 1 is. It's this weird 0 over 0. So let's see if we can at least figure out where we're heading. So I'm going to get out my graphing calculator and go to y1 and plug the function in here. So I've plugged this in using parentheses, and now I'm just going to zoom 6 this one. Zoom 6 to get my standard window. And we want to know, as we get closer and closer to the x value 1, what's the y value? So let's go ahead and trace this. And as we move closer and closer and closer and closer and closer to the x value 1, it looks like the y value is also approaching 1. Let's also take a look at a table. So I'll just put the graph here. But now let's look at a table. So I'm going to make my table set, let's see, so second table set. I'm going to make this start around, let's start it at 1, because that's the value we're interested in. And I'm going to make my deltas go by, let's see how close we can get. Let's do 0.001. And now go to table and see what we come up with there. So if we go a little bit before and a little bit after 1, we're very close to the x value 1. The y values also appear to be getting very close to the y value 1. At 1 itself, we get an error, and that's not surprising, but we're definitely approaching 1 on the y values as we get closer to 1 on the x values. So we can at least say y is approaching 1, which is kind of interesting. The idea that we've just seen in action is the calculus concept of a limit. A limit is the y value that a function approaches as the x value approaches a certain value. So we have a special notation for this. We write limit as x approaches something of some function equals some number. What we're basically saying by this craziness is that as x gets really close to a, this function f of x is getting really close to this y value L. So using our example that we saw in the warm-up, we could say that the limit as x approaches 1 of x squared minus x over x minus 1, the limit of this equals 1, because as the x values get really close to 1, so does the y value. Now, we've just seen that using a table is one way to figure out limits, but that's not always available. And we're not going to really deal with algebraic limits just yet anyway. We're going to focus on the graphical ones, but this is a good start. Now, in our exploration of limits and trying to figure out how to find these limits, one important question is the relationship between a limit and the value of a function at a certain x value. Let's explore that using these two examples. So, pause the video, and using the concept of a limit and what you know about functions, see if you can find f of 2 and the limit as x approaches 2 of the function represented in this graph. All right, let's see how that worked out. So f of 2, we just have to go to the x value 2 and look up the y value there, and that's going to be 3. That's just a normal function evaluation. The limit as x approaches 2, this is the y value that our function is approaching as we get closer to 2. If we look at the function as we get closer to the x value 2 from the left or from the right, we are approaching the y value 3, so the limit as x approaches 2 is also 3. So we see here that function values and limits at that x value can be the same number. Let's take a look at this one over here. Pause the video and take a moment to try this one out. All right, so f of 2 on this one, that is the solid dot when you plug in an x value of 2. That's going to be all the way up here. This is the y value 5. And again, the limit as x approaches 2, if we follow the function, we're getting closer and closer to the y value 3, both from the left and the right side here. So it appears that function values and limits don't have to be the same. So the limit and the function value at a are sometimes equal, but they don't have to be, and that's important to keep in mind as we go. Let's take a look at this interesting graph now. If we ask for the limit as x approaches 2, well, this is an interesting situation because as we approach from the left side, we're approaching one y value. As we approach from the right side, we're approaching a different one. So this gets us into the idea of having a one-sided limit. A one-sided limit is just the limit as you approach from only one side, and we have different notations for these. Right here, the limit as x approaches a with a little negative up here, this is saying as I approach from the left side. If we want to approach from the right side, it's kind of the same idea, only we'll have a little plus up here instead of a negative. And these minuses and pluses tell us which side we're approaching from. So for example, if I ask for the limit as x approaches 2 with the little negative up here, well, now I'm asking about what y value am I approaching from the left side as x gets close to 2. So following this from the left side, we've got the y value 3. And by the same token, we could ask about the limit as x approaches 2 from the right side. Pause the video and see if you can figure that one out. So approaching from the right side, we're approaching the y value up here. That's 4. Now, if there's one-sided limits, you might be thinking, well, there's got to be two-sided limits, and there are. A two-sided limit is the limit that we're approaching as we approach x from both sides. So when we say we want the limit of a function at a certain number, and we don't write any little pluses or minuses, this is what we're talking about, is this two-sided limit. Now in this case, since we're approaching different y values from the left and the right, if the limits are not equal, we would say that the limit does not exist, and we abbreviate that often to DNE. We're going to take a look at these two graphs now. Here we're going to explore the question of whether a limit existing and the function existing at a value have to be one and the same thing. So pause the video and try out each of these two examples, and then see if you can fill in these blanks. All right, let's see what we came up with. So for example 4, f of 2, if we look here, we have an open dot. The function itself does not exist at 2, so that is DNE, or undefined. The limit as x approaches 2, from the left side and the right side, we are approaching the y value 3. So the function not existing didn't stop the limit from existing. Let's see if the reverse is true. Over here, f of 2, we've got two different dots. We have to go with the solid dot. That would be the y value 4 up here. And then the limit as x approaches 2, well, from the left, we're approaching the y value 3. From the right, we're approaching the y value 4. Since the left and the right can't agree, we would say DNE for that limit. So the function existing somewhere did not stop the limit from not existing. So let's take a look at these two questions now. If the limit exists, then f of a, does it have to exist? Well, we see here that it doesn't have to exist. It can exist. If this were a solid dot, then they would both exist. So this is a sometimes right here. Now, if the function exists, what about the limit? Well, looking over here, the function existing didn't mean the limit had to exist. But again, if the function and the limit were the same number, then they would both exist. So here, this is also a sometimes. So really, we can't make any conclusions about the function value based on the limit or vice versa. Here's another graph to give you a little bit more practice. So pause the video and try to find each of these things or say that it doesn't exist. All right, so we've got the limit as we approach a from the little negative here means the left side. So going from the left, it looks like we're approaching the y value 2. Next one, going from the right side, we are also approaching the y value 2. Now remember, when you're doing the two-sided limit, that's the little a here with no plus or minus, the left and the right limit have to match for that limit to exist. Here, since both the left and the right side limit are the same number, we can say the two-sided limit is also 2. And then finally, f of a, that's just the function value at a. Since that's an open dot, we're going to have d&e for that, undefined. Alrighty, try this next one on your own. So, left side limit, approaching a from the left here, we're approaching the y value 2. From the right side, we have to go from the right side here, we're approaching the y value 3. For the two-sided limit, since the left-sided limit and the right-sided limit do not match up, they are not equal, we would say that the overall limit is d&e. And then f of a, that is the solid dot if one exists at the x value a. Moving up here, we see that happens at 3. And at this point, we have reached our limit for this lesson. Until next time, Mr. Sutton signing off.